Welcome back. In this video, we are going to look at discontinuities. And as a first exercise, before we get to the different types, we have this function, and it is a function, despite what you might believe. And we just need to identify whether it's continuous or discontinuous at each of these particular x values, okay? And so what I'm going to do is I'm going to do a little abbreviation. So I'm going to say continuous is abbreviated with CTS, and then discontinuous is DTS. Okay, I could do DCTS, whatever. Okay, but here we go. So I'm looking at each of these. So at x is equal to 3, right? So this is minus 3. I should maybe label these for a little bit of reference. So I'm going up here, and let's see, here I am looking at f of a, right? And as I approach from the left, I get closer to that f of a value, and as I approach from the right, I still get close to that f of a value. So this one would be continuous. By comparison, at x is equal to minus 2, right? Here's minus 2, right? As I go to negative 2 from the left-hand side, I extend forever downward, so that's going towards minus infinity. Going from the right, same sort of thing. So I would be tempted to say that the limit exists, right? Because the left hand, right hand limits agree in concept, right? But what's f of a, right? I don't have f of a, so for that reason, since the f of a doesn't exist, right? So just remember, continuous is the idea that limit as x approaches a of f of x is equal to f of a, right? If I have the right-hand side not existing, then can I have it be continuous? No. So I'm going to do DTS, okay? Or DCTS, however you want to abbreviate it, okay? So now pause the video, try the others, and resume the video when you're ready to see the answers. Then magically the answers appear. So at -1, it is continuous, right? Left and right hand limits agree, and the function exists. 0, it doesn't. It is discontinuous because the function value, the right hand side, is different than the left side. 1, it exists, and 3 exists. 2, it has that piecewise behavior, so it is discontinuous there. Okay, and so when looking at these different values of x, right, we saw different things happen where we got points of discontinuity. And so the types that we saw can kind of be put into 3 different categories. Okay, so let's just make a quick little sketch. So there's jump, infinite, and removable discontinuities. Jump would be something like we see a hole happen, and then we come down here, and then we maybe continue on. Okay, so it's piecewise like behavior. Okay, it's on the left side of A, it's one thing, on the right side of A, it's another thing. Removable would be what we saw at x equals 0 in the above example. So something like this, where we have a hole and then the function value is above or below it. It's just not equal to what we would expect. And then infinite was the case where we had like vertical asymptotes appearing. Okay, so, and the example we saw was more like that, right? So that would be another situation in which we would have a discontinuity. Okay, and now the one example that we began with, that was very graphical in nature. Here are more algebraically defined functions, and so let's see if we can figure out what is going on here. Okay, so in f, right, this is the floor function. Floor of x, okay? This is the greatest integer. So for example, 1.9 would just give you 1, and 2.1 would just give you 2. Okay, so you chop off the decimal. Okay, so if we think about this, would this be continuous? Well, no, because we'd have something, if we were to graph it, for all the values between 1 and 2, it would be like this. And then as soon as we get to 2 to 3, it would look something like this. And so we're going to see holes appearing. Okay, that would be solid. Okay, so this is no. Okay, and then I would say it's discontinuous at x is equal to an integer. Okay, the set of integers is z. Okay. This next one, is this continuous or not? So again, we might need to play with this a little bit, pause the video, try it out on your own, but we have to remember that we have to implement some algebra skills. So this would factor as x minus 2x plus 1, and then that would reduce and then give us just x plus 1 at all values that are not 2. Okay, so then now if I look at the limit as x approaches 2 from the left of g of x, g of x, that I'd have to use the first branch, so that would be still just 2, and then this actually ends up being the same as limit as x approaches x approaches 2 from the right of g of x. You can check that on your own. Okay, and sorry, it's not 2, it's 3. Okay, there we go. I got writing too many 2's. So this also happens to be the same thing as g of 2. Okay, yep. And so then therefore we get it to be, we can say that g of x is continuous at x is equal to 2. Okay, triangle of dots, you might not have seen that. It just means therefore in mathematics. Okay, next one. So now the terminology here might confuse you a little bit. H of x is 0 if x is within the irrationals. Okay, Q complement. Q is the set of rationals. And then, so when we have a rational number, h of x is going to be the value of 1. And then when we don't have when we have an irrational, right, something that's not rational, it would be 0. Okay. And so this one, you can imagine it's going to look a little wonky. Like if we try to visualize it, it's not going to be pretty, but it'd be something like, like we have infinite many dots at 0 and 1. Okay, it looks a little wonky, but the point is it continuous? Well, no, it's jumping all over, right? So this is going to be very discontinuous. Okay, and it does say, you know, the type. So this is a jump discontinuity. I should actually mention that in the first one for F, continuity spelling at, so it's jumping at every value of x that is a rational or irrational, depending on what you want to say. Okay, and this just means in. So for x, a rational number. Okay, so with discontinuities, again, they fall into 3 general categories: jump, removable, infinite. You might have to identify which one. And then note that you might have to identify it in an algebraic context or a graphical context.